Då hoppas jag att ni ser vår presentation. Och jag hälsar än en gång välkomna till det här webbinariet. Som ska handla om ett projekt som heter Elektrolysassisterad förgasning av biomassa för drivmedelsproduktion. Jag heter Emmy Bogan, som jag sa. Jag är kanslikoordinator för samverkansprogrammet Förnybara drivmedel och system och F3, Svenskt kunskapscentrum för förnybara drivmedel. Vi spelar in det här webbinariet och det kommer finnas tillgängligt på F3s YouTube-kanal inom några dagar. Lite praktiska saker att förhålla sig till. Ha i alla fall din mikrofon avstängd. Slå på den om du vill säga någonting. Givetvis ha gärna kameran avstängd om du inte pratar. Och har du problem med uppkopplingen så kan det vara ett trick att stänga av inkommande video. När vi har vår frågestund lite senare så kan man antingen ställa frågor i chattfunktionen. Det kan ni göra under tiden presentationen pågår och så läser vi upp dem efteråt. Eller så använder ni räck upp handen-funktionen. Som jag sa så samlar vi frågorna till efter presentationen. Och om ni har några tekniska problem så ska jag försöka hjälpa er med det också parallellt med detta. Så skriv till mig i chatten, jag tror att det är lättast. Vi kommer också att lägga ut presentationen direkt efteråt på F3s webbplats. Programmet ser ut så här. Jag kommer att hålla en liten introduktion och berätta om samverkansprogrammet Förnybara drivmedel och system. Och därefter så lämnar jag ordet till Sennai Asmelash Mesfun som kommer att presentera resultaten från projektet Elektrolysassisterad förgasning av biomassa för drivmedelsproduktion. Vi avslutar med en frågestund. Nu då kort några ord om samverkansprogrammet som det här projektet då har genomförts inom. Det är ett program som pågår nu till årets slut. Det är dess andra etapp och ett samarbete mellan Energimyndigheten och F3, då Svenskt kunskapscentrum för förnybara drivmedel. Den totala budgeten har varit 44 miljoner. 22 kommer från Energimyndigheten, 11 från F3s parter och 11 som samfinansiering i projekten som pågår. Alla medel är tilldelade och totalt så finns det 26 projekt inom det här programmet, den här etappen. 5 stycken är för närvarande avslutade och det kommer att komma ganska mycket resultat inom det närmsta året. Syftet med programmet är att ta fram analyser som kan stödja vetenskapligt underbyggda beslut. Därför att systemförståelsen hos politiker, myndigheter, industri och andra organisationer om hållbar energiförsörjning för transportsektorn behöver öka. Och det här vill vi bidra till. Det finns ju mål om minskade koldioxidutsläpp och på sikt fossilfrihet i transportsektorn. Och programmet bygger på stark samverkan mellan forskningsutförare, industri, institut, näringsliv och andra relevanta aktörer. Till exempel regionala och nationella myndigheter. Hittills då, som jag sa, så för närvarande så pågår den andra etappen. Totalt sett så har 55 forskningsprojekt genomförts eller håller på att genomföras inom programmet. Och hittills har det gett 38 vetenskapliga publikationer. Vi har haft 7 öppna... Nu ska vi se. Ni får gärna stänga av mikrofonen. Vi har hittills haft 7 öppna konferenser och kommer att ha en 8:e i höst. En programkonferens. Och antalet deltagande organisationer i projekten är ett 80-tal. Så det är en bred grupp som samverkar i det här programmet. Några ord kort om F3. Vi är också en vad ska man säga, samverkans- och nätverksorganisation där vi samlar industri, högskolor, institut och myndigheter som delar synen på långsiktigt hållbar drivmedelsförsörjning till transportsektorn. Och detta är våra parter. Det är då en grupp med en akademigrupp, Lunds universitet, SLU, KTH, Chalmers och Bio4Energy som är ett samarbete mellan Umeå universitet, LTU och SLU i Umeå. Sedan har vi industrigruppen, Lantmännen, Preem, Neste, E.ON, Scania, ST1 och Volvo. Vi har de 3 stora forskningsinstituten på området, IVL, RISE och VTI. Och då samarbete inom samverkansprogrammet med Energimyndigheten och för övrigt inom F3 med Västra Götalandsregionen. Och jag ska säga att vi har då ingen politisk agenda och vi ägnar oss inte åt lobbying eller något sånt där. Utan det här är helt och hållet samverkan och kunskapsbyggande som är i fokus. Centrumvärd för F3 är Chalmers industriteknik. Och här driver vi ett kansli som består av föreståndare som är Ingrid Nordgren, jag som är kanslikoordinator och seniora rådgivare. Och ja, som jag har upprepat flera gånger redan är att F3s viktiga uppgifter är samverkan, kunskapsbyggande och kunskapsspridande. Och det är ju kunskapsspridande som vi ägnar oss åt idag. Har ni några frågor eller vill komma i kontakt med oss så går det bra att kontakta antingen mig eller Ingrid Nordgren, vår föreståndare. Ni ser uppgifterna här och de finns på vår webbplats också. Och jag uppmuntrar er att anmäla er till vårt nyhetsbrev. Då återgår vi till programmet här. Vi ska strax få lyssna på Sennai Mesfun som ska hålla sin presentation och det kommer han göra på engelska. Och den efterföljande frågestunden kommer också att vara på engelska. Avslutningsvis då, här har vi lite korta fakta om projektet. Projektledare då, Sennai på RISE. Vi har deltagare från Bio4Energy, det är Andrea Toffolo. Från KTH har vi haft Claes Engvall och Carina Lagergren. Och vi har också haft medverkande från Cortus Energy. Projektet avslutades nu i december 2020 och den totala projektkostnaden har varit ungefär 1,2 miljoner. Finansiering då har kommit ifrån Energimyndigheten, F3s parter och de deltagande parterna i projektet. Och rapport och en executive summary som vi kallar det, lite mer lättillgänglig sammanfattning av projektet hittar ni på vår webbplats. Så med de orden, and I will switch to English now. I will ask Sennai to start sharing your presentation and please, when you are ready, just go ahead. I can remind you also already if you have questions, please write them in the chat or save them for the questions sessions. Thank you.
Yeah, thanks, Amy. Welcome everyone to this webinar entitled Elektrolysassisterad biomass gasification for biofuels production, a techno-economic perspective. This project was a collaboration between RISE, the Royal Institute of Technology, Luleå University of Technology, and Cortus Energy. That being said, I would directly go to my presentation. Some background here. a generic biomass-based, biomass gasification-based transportation fuel production is shown in this slide. And one of the challenges with biomass gasification-based biofuels is that the gasification process scalability compared to the downstream process, for example, the water gas shift and the synthesis processes, which are commercially developed based on coal feedstock. So there is still some challenge with the biomass gasification technique when it comes to scalability. And depending on the gasification technology, there could be also multiple process steps involved that complicate further the process. So it would be, of course, of interest to have techniques that can improve the productivity without having to scale the gasifier are of interest. In doing so, if there are also techniques that can replace part of these downstream processes that complicate further the process are also, of course, of interest. And in that regard, this project looks at electrolysis-assisted biomass gasification, where an electrolysis process sort of integrates in the system, if possible, also reduces some of the downstream processing required in doing so. And also co-produces, of course, some of the internal required oxygen is an additional incentive. But the most important aspect of integrating electrolysis process with gasification is, of course, to increase the productivity without having to introduce additional carbon source, or in other words, scaling up the gasification step. And this project specifically looks at that, and at what cost, to what extent can the product will be boosted without additional carbon source, and either a possibility to reduce also some of the process steps in a conventional gasification-based process. So in order to frame this, we have defined objective, which is to investigate a molten carbonate electrolysis cell for syngas conditioning. How far can this take us when it comes to improving the productivity, reducing some of the process steps, and at what cost can that be achieved? And another additional advantage or benefit to look at is to what extent can we link up electricity into producing liquid fuels in the context of power to liquid in this case. So in order to frame this study in a system perspective, we have opted to integrate a sustainable aviation fuel production facility at a generic sawmill as a host facility. In a typical Nordic sawmill, about 50% or half of the incoming timber ends up in the byproduct stream, and the remaining half becomes the final product lumber. And in a business as usual operation, this byproduct would be exported largely to other forest industries, such as pulp mills in form of wood chip and wood pellet plant in the form of sawdust. And part of it is being internally used for generating the heat required for the lumber drying process. But with this integrated case, this product is set to be upgraded on-site into sustainable aviation fuel, and the heat requirement of the sawmill can be partly satisfied from the secondary heat produced at the SAF facility. And if that is not enough, then still part of the biomass can be combusted to supply the deficit as depicted in this picture. But central to this, of course, is integration of the Mcsc in that gasification-based SAF facility, as is since Mcsc is the technology that we decide to study further in this project. So it will be, of course, important to say a few words about it, its operational parameters, and what our model was based on. So we have developed an Mcsc model based on previously conducted experiments in the Royal Institute of Technology at a lab scale, and some operational data was achieved from those experiments and extrapolated to develop a model for this project. The picture on this slide shows the operational principle of the Mcsc, some of the major chemical reactions that take place in the cathode and anode side of it. So of course, as is the case for most electrolysis process, polarization curve is very important, which is the voltage current curve. The stack temperature is also of importance in this case, especially since the carbonate cell is operated using lithium or potassium carbonate, which should be in a molten phase, so the temperature is fairly high. So we wouldn't want to supply external heat. We would like to maintain the unit at the temperature that can keep the electrolyte in a molten phase. And the potential to recycle CO2. I'd like to start my pointer. So as you can see here, the exhaust from the anode is a mixture of oxygen and carbon dioxide in the ratio 1:2. So one would like to recycle as much as possible of this carbon to the unit in order to improve the productivity or the yield of hydrogen and carbon monoxide, which later is upgraded into transportation fuel. So I would mention quite a lot CO2 recycle in the coming slides. When I say that, I would be referring to this one, recycling from the anode to the cathode exit. Of course, this stream undergoes a cryogenic separation process before the CO2 can be separated. Here is a typical voltage current polarization curve to the left for different carbon recycle rates, 0 to 50%. It can be higher. And the main message from this picture is that from power use perspective, one would want to be on the lower end of the curves where the power consumption is low. And from stack size or the capital cost for the unit, one would want to be on the high end of these curves where the current density is high, which means that there is high power consumption. So when it comes to Mcsc, power use and stack size are kind of contradicting objectives. The other aspect is, of course, as I mentioned, stack temperature, and there is no strange relation here. The higher power consumption leads to higher stack temperature. Of course, to higher density. But when it comes to methane, which is a key component in the syngas, depending on the downstream process, for example, if synthetic natural gas is the final product, then pronounced methane in this unit could be of interest. But if FT is the upgrading technique, then methane is not a desired product. So it's good to study that as well. And as you can see, we have tracked the methane content of the cathode exit versus the current density. So higher current densities, which lead to higher temperature, which lead to lower methane content in the cathode exit. Nonetheless, for all the cases we have evaluated, there is some methane left in the system, which means that if we are going to do FT upgrading, and if we want to have high productivity, some reforming would still be needed in this case. Here is just methane against stack temperature, as I mentioned earlier, higher temperature, lower methane. That's the relation there. With that, I would like to present the cases we have specifically evaluated in this project. We have evaluated 3 gasification technologies, each of which has 20 megawatt lower heating value syngas capacity. The first technology was the wood roll technology developed by Curtis Energy, a dual fluidized bed configuration similar to the Gobi gas plant in Gothenburg, and a bubbling fluidized bed directly heated with oxygen as fluidization medium, which was similar to those developed by Andritz Carbona. And as I mentioned earlier, since FT was our way process, we would like to reform the syngas a little bit in order to reduce its methane content. And for that, we have considered 2 process configurations. One is a traditional steam reformer that sacrifices part of the gas to the reformer in order to supply the heat required to drive it. And another one is more advanced technique, currently under development, electric heated steam reformer. The electric heated steam reformer kind of saves carbon loss in the reformer, as it doesn't sacrifice part of the gas. Instead, the reactor is heated with electricity. And in the economic aspect, we have looked at the investment and production costs as indicators for the cases studied. So this is typical configurations as an example presented here. As I mentioned earlier, a sawmill will result in about 50% of the incoming timber as byproduct. And our target here is to upgrade the mixture of sawdust, wood chips, and bark into a final FT, but the intermediate step in the gasification process is the one that scales the whole thing. As I mentioned earlier, is in 20 megawatt syngas is our target. So in case we run into steam deficit in any of these process steps plus the steam demand of the sawmill, then we have a biomass boiler that combusts part of the biomass in order to supply the process steam. And in comparison to a conventional gasification-based technique, the main difference is that the Mcsc replaces the water gas shift of a conventional process. And in doing so, our main contribution is that we can capture part of the carbon dioxide already by the Mcsc, which kind of unloads the carbon separation requirement afterwards before the FT upgrading in acid gas removal unit. That's one benefit here. The other one is, of course, we retain as much as possible of the carbon that a water gas shift would have lost in the syngas stream and increase the productivity. And these configurations led into FT liquid production of 14 to 18 megawatt from 20 megawatt syngas feed. And the difference between the conventional steam reformer and the electrified steam reformer resulted in about 9 to 13% increase in yield of syngas, depending on the scenario or the gasification technology. And these figures, the yield of FT liquid is about 55 to 60% on lower heating value basis to the biomass which is fed to the gasifier, compared to a traditional or water gas shift based gasification process, which results in 45 most, and in some cases about 50% FT yield. So the yield of FT in this case is much higher. And this is thanks to the Mcsc, of course, at the cost of additional electricity that is fed to the process. But we will come to that and we'll see how the economics look like with this new process. And one of the limitations here one should notice is that we are limiting ourselves to the carbon that comes with the biomass. So one can add, of course, additional carbon or external carbon source to the Mcsc and even increase further the yield without introducing additional biomass via the gasification step here. So I thought it would be, of course, interesting to check our system from carbon balance perspective so that one can identify where we are losing most of the carbon, and we can think about that at a later stage too if we want to improve further the yield. And for that, here I present a Sankey diagram for carbon balance in the different process steps. This is as an example for the dual fluidized bed case. And the one to the left is referring to the conventional steam reformer scenario. And as you can see, from the incoming biomass, this is the carbon balance normalized to the carbon in syngas. So about 31% of the carbon is already lost generating the heat required to drive the gasification process. So this 31% doesn't even get to the Mcsc. So there is a very limited window that the Mcsc can contribute in this case. And that's why the increase was not that significant when it was for the dual fluidized bed. If we look at or compare it against the Babylonian fluidized bed case, where the carbon loss in the gasification stage was only 11%, then you can see the contribution of the Mcsc was quite magnified, and it contributes both in terms of fixing carbon into the system as well as capturing carbon and reduces the load on the AGR unit. All at the same time, it increases also the yield of FTP. So this kind of presentations really point us in the direction where we are losing most of the carbon and what we can do about it. With that, I would jump to the economic performance, and here I present the most relevant economic parameters: cost of biomass, electricity, oxygen, scrubber oil, which only applies for the dual fluidized bed configuration, and some economic assumptions here. An annuity factor of 0.1 was used to annualize the capital cost. This corresponds to 20 years economic lifetime and 8% interest rate. And a generic operating and maintenance factor, 3% of the total fixed capital investment was applied for all cases. And based on these economic parameters, we have arrived at a production cost over the total FT. As you know, with every FT technology, there is a wide spectrum of products. It produces diesel range hydrocarbons, SAF or aviation fuel hydrocarbons, and small fraction of gasoline range hydrocarbons. So we are taking the cost in this case over the total FT yield. And we arrived at a cost between 1,400 to 1,550 here, Swedish krona per megawatt hour. To give you some perspective, the current market for HVO diesel is around 1,200 Swedish kronor per megawatt hour. Compared to that, we are off by about 300 Swedish kronor per megawatt hour over total FT yield. But since our target was sustainable aviation fuel, which the technology that we selected for the FT produces about 60% SAF from the FT liquid, and assuming, of course, an income for the diesel and gasoline range fractions using 1200 Swedish kronor per megawatt hour, then the production cost slightly increases by about 150 to 200 Swedish kronor when we allocate all the costs to sustainable aviation fuel only. To put it into further perspective, I have compared the results to the investigation carried out by Maria Wetterstrand in 2019 about sustainable aviation fuel production in Sweden. And according to their investigation, they arrived at costs for 2021, which is shown by the green bar, and for 2030, which is shown by the blue line. And compared to that, our results are in all cases between the two ranges specified in that investigation. And as you can see that most of the production cost derives from the capex, which is about 55% in most cases, the blue bar. So the system is highly sensitive to that, and I introduced a sensitivity on the total capex, 30 plus or minus 30, and the error bars show where the production cost depending on the factor. So, well, in general, would remain below the estimated for the year 2021 for SAF production. With that, I will jump into some concluding remarks. Depending, of course, on the gasification technology, the activity of the Mcsc has varied quite a bit. For example, the wood roll and the dual fill diazide bed, both of them are steam gasification processes, which means that the syngas produced by this process was close to hydrogen to CO ratio that is optimal for Fischer-Tropsch upgrading. Whereas the bubbling fill diazide bed, it was far away from the optimal. It was around 1, if I remember it correctly, which means that the activity of the Mcsc in order to reach a hydrogen to CO ratio of 2, which is the optimal for FT conversion, was significant. So the activity for the bubbling fill diazide bed turned out to be quite significant. And the syngas yield increase by 15 to 31% was achieved compared to a water gas shift based biofuel production via gasification process. And the higher end of the range is for bubbling fill diazide bed, and the lower range of the range corresponds to the wood roll process for the same reason I already described. And for the same size or for a given size of the Mcsc, if it's run under low current densities, it will result in low stack temperature, which means that it will pronounce the methane content of the syngas, which is really not good for FT upgrading, but could be attractive, for example, if the final product was synthetic natural gas. In this case, it would be already producing some of the required product at the Mcsc stage. But this will require, of course, pilot scale experiments and what the impact of the methane to the cell would be, and to what extent can it, of course, operate normally under methane load. As I said, it's always good to identify the process steps where the carbon is being really lost. For example, for the dual fill diazide bed and the wood roll cases, we were losing most of the carbon already in the gasification step. So at a later stage, when we integrate the Mcsc, it was a bit late to recover some of this carbon. So it could be worth, of course, checking to use electricity in some form already in the gasification step to heat up some of the processes. For example, to generate the steam required for the gasification process in using an electric boiler could be one way to look at it. The process turned out to be, of course, capital intensive. About 55% of the production costs derived from the capex, and of that 55%, the 35% derives from the gas conditioning section that included the Mcsc, of course, which means that it shows the process still is at the early stage, and it will take some technology learning, some pilot scale testing to confirm some of the model results as well, in order to certainly state these numbers are reasonable. And yeah, thanks. This is what I have prepared. It seems I have finished it a bit early, but it's better to be early than late. Back to you, Amy.
Yes, thank you, Sennai, for an interesting presentation and with perfect timing. I see we will move directly into questions, and I see that we received one in the chat. I don't know, Stefan, would you like to ask your question, or is it okay if I read it?
I can do so.
Yeah.
Hi, Stefan. You showed these sensitivity or trade-off for operating of and capex of the Mcec, the carbonate cell. What points did you choose, or how did you choose operating points in the FT framework then? Was that was the fixed points you had, or did you do some kind of?
Yeah, we did an iterative approach, but at the end, of course, you have to end up with 1 point in the model. But you see, for all these points, we have derived the syngas composition basically for all the points shown in this figure. Then what we did was that we have evaluated, of course, if you have noticed it, even in the results, there are 8 scenarios, for example. As you can see, the bubbling-filled bed, for example, it has two cases. One is with high yield, which means that we don't really care about how much electricity we use in the process. We just care about to boost the yield of FT. The other one would be like optimum, which means that, okay, we go for optimal point where the electricity consumption is okay and the yield is okay, sort of say. So yeah,
I mean, optimal from an economic perspective.
Yeah, exactly. So it's kind of we have done that, for example, for the bubbling filled bed, where the Mcc activity was quite high, as I showed by the results, but we didn't do that for the wood roll and the dual filled bed. But essentially, for all the points shown in this map, we have derived the syngas composition, and we kind of tried to select the optimal for FT, where the hydrogen to CO ratio is necessarily 2, and the methane content was low as much as possible.
Thank you. I will leave the word to Lars, who has a question, if you would like to say it yourself.
Yes, hello, Lars Waldheim here. I missed, thank you very much, Sennai, for this presentation. Interesting and very good. But I missed the figure on how much electricity do you actually use in relation to the 20 megawatts of biomass you started out with?
Well, because now, okay, there are multiple points. As indicated here, there are multiple points. For example, if we are referring to the electrified SMR, and there is a cryogenic separation that takes electricity as well, and then the Mcc itself. So But most for the highest case, it was for the bubbling fluidized bed, and it was around 6 megawatt for the MCC alone. I don't really remember the numbers for the cryogenic separator and electrified SMR cases, but I mean, we can look at the contribution of costs from electricity also, of course. It can tell some story by itself. So this is kind of the aggregate electricity for all the units. But I think it was around 6 megawatt for the bubbling fluidized bed, where we opted to maximize the yield at the cost of increased electricity use. It was 6 megawatt for that case. So
that would be the highest.
That is the highest.
Violet bar. Number 4 from the right-hand side,
exactly.
Right?
Yeah.
Okay.
This is the bubbling yield, and then this would be the case. Yeah.
Okay. Thank you very much.
Yeah, but if you go to the report, you'll find all the numbers in table format. So, yeah.
Yeah, I have read the report, but I didn't sort of pick up on this number at the time. But
yeah,
so
but they are
I'll
available.
go back to it.
Yeah, perfect.
Thank you.
Thanks.
Thank you, Lars. I see Joachim Lundgren has raised his hand. Please, Joachim.
Hi, Sennai, and
hey,
thanks a lot for a very nice presentation.
Thanks.
Good to see you again. Long time.
To see you, yeah.
I find this very interesting, actually. And but are you aware of any commercial suppliers of the MCC, or is it still just research units? And that was one. The second question is, I mean, how this is of interest, and are you planning any next step, and if so, in what way do you plan to continue?
Yeah, nice. This is really good questions. I think when it comes to MCC, still it's lab scale units, research level that I come across when we were doing this project. But on the other hand, the electrolysis mode, the fuel cell mode, there are some pilot scale, if you can call that, around 3 megawatt capacities available, especially in the UK, because they are looking at this also in the direction of carbon capturing technique. It's not only about producing electricity, but it's about capturing carbon dioxide as well when it comes to fuel cell mode. So in that direction, I see there could be potentially high-level investigations being carried out that I know of in the UK to integrate them at industrial sites for carbon capture. But for us, the next step, I would say, would be to be able to test this at a pilot scale level with actual syngas, because now the experiments are being conducted mostly under simulated syngas. So it will be, of course, syngas contains a lot of contaminants, and that would be, of course, of interest to test this unit. How far can it take us? How far of these particles can it tolerate? So I see the next level to be that pilot scale experiments conducted on actual syngas from biomass gasification. And that's what we have discussed with class, of course. Probably that could materialize since they are the leading institute in this technique.
Good, thanks. Very much looking forward to a continuation and with more experiments. Very good. Thanks.
Yes. Thanks.
Thank you. Great questions. I also actually had prepared similar ones. Is there any More questions from the audience? No, not at, yeah, somebody raised their hand. Stefan, please go ahead again.
Yeah, just wondering when you recalculated the costs to aviation fuel only.
Yes.
Did you, or maybe that was included already in the basic calculation, is there an upgrade of the, or a separation of the different components, or did you just do a numeric exercise recalculating, allocating some revenues for the byproducts, or did you add like splitting up the streams to actually have the pure products like diesel, gasoline, fraction?
Yes, because yeah, that's a good question. We have some. We have some data from developers, actual technology developers on that. At least we evaluate how much hydrogen is being required, and different fractions of the hydrocarbons are certainly kind of calibrated based on technology developers' data. But apart from that, of course, it's a numerical exercise. Yeah, but at least the hydrogen consumption and the fractions are kind of calibrated to actual data.
Okay, thanks.
Thank you. I see Joachim, you have another question?
Yes, my final one. It's the capacity. I mean, for a Fischer-Tropsch production unit, this is fairly small production capacities.
Yes.
Do you see any limitations in scale up with the Mcsc? I mean, how large plants can you build in a commercial scale? Do you have any?
Yeah. Well, of course, as you know, for FT, as you said, this is quite a small scale, and I don't see, apart for the gasification part, I don't see any problem with the other units being scaled up, especially when there is external carbon source that can, of course, boost up the productivity of final products. For example, external carbon dioxide can be used in directly supplied to the Mcsc with steam, and then that part of the process can be scaled up independent of the gasification step. So that way, there is, of course, that could also improve the process economy. One of the reasons for this relatively high production cost is, of course, the small scale in the FT and also the Mcc unit itself. So maybe this is not really small for gasification, 20 megawatt, but for the other process unit, it's certainly quite small. And considering such configuration is, of course, a way to scale up this process independent of each other. And I don't see any reason why we cannot go higher for the later stage, at least. I don't see a reason for that.
Thanks.
Thank you. I had a question, since we're discussing advantages and disadvantages of this technology. Beyond the high costs, do you see any disadvantages with the concept in the whole, and what are those in that case?
But when you say disadvantages, is it in comparison to water gas shift, for example, or is it?
No, I would say no. Maybe just like pros and cons. Then maybe not the disadvantages, but pros and cons.
Yeah. Well, one of the not if I don't know if you can call it a disadvantage, but it is to confirm these model results at the pilot scale is a key step, which is one of the really weak links at the moment. It's only based on lab scale, and we don't know really what will happen when you apply actual syngas with a lot of contaminants in it. That is the weak link here. Apart from that, I think the other techniques are quite commercially available, and I don't see any problems from those sections.
Thank you. So we hope that you get to continue this then and test it on a pilot scale and see what comes out at that step.
Yeah, I look forward to that.
Yeah. Let's see. We have another question now from Chuang Su. Please go ahead.
Yes, thank you. I have one question about, because we talked about a lot about the prospect, the commercial prospect of this technology. I think this is new for me. Could you tell me what's the critical barriers or critical issues for the future R&D work of this technology? Yeah, thank you.
Yeah, well, I myself do not really conduct experiments. I cannot call myself really expert in that, but as I said, our data is based on lab scale experiments, and the tests were made on artificial syngas, which is quite different from actual syngas, and that's the process. Like the technology development requirement of this technique is really in that direction at a larger lab pilot scale plus actual syngas from biomass gasification with with all of its contaminants, and test the unit if it can handle that and to what extent can these numbers be confirmed based on such activity would be, of course, the next R&D work for the Mcsc. But for the rest of the process, as I said, there are technologies that are commercially available, so there is no need for additional R&D work on those.
Thank you. Is there anyone else? Otherwise, I will move forward with another question from us here at the office. You write in the report that this technology boosts the overall carbon efficiency and increase the product throughput. However, the electricity demand increases, and from a Swedish perspective, and considering that we want more electricity for the industry as a whole, what are your thoughts on that, like electricity use or supply versus demand?
Yeah, well, actually, this can be also a benefit for this kind of technologies if you look at it in terms of, for example, integrating intermittent power into the Swedish power system. Then such processes can be, of course, of interest to take advantage of excess power, or when the power load is low. These technologies can be take advantage of that scenario. And in this study, we don't specifically consider the electricity to be freely available. We have put a fairly high cost in order to indicate that. But this is in no way to compute for electricity with other industries. This is rather to like run in parallel and allow integration of, for example, further wind energy into the electricity grid, so that when there is excess electricity available, such units can take advantage of that and produce storable liquid fuels for further use in transport, or it could be also for industry. Because these fuels can be used also to generate electricity when the demand is high. So this can be seen as a storage rather in that case.
Okay, thank you. So I also have a last question, and this is a question that I'm passing on that I got from someone. So I will try to do my best to interpret it. It concerns the electrolyzer. if you wish to scale up and expand the concept, how is it made concerning the electrolyzer? Do you need to replace that with a bigger one, or is it rather like a modular approach in which you add more electrolyzers?
Well, I really don't know the technical specification of these techniques, but as is the case with most electrolyzers, I think it should be possible to build it so that it can be used in a modular way. I think it should be possible to do that because it can be compartmentalized into a modular way, I assume, but this is just from my head. I don't think I'm the expert for that.
Okay, let's see. We have, we'll take a last question. It's from Johan Westin. Please go ahead.
Thank you. Maybe I missed it in the presentation, but what is the overall capex assumption, and also if you just indicate what are the distribution between the gasification and syngas preparation versus the Fischer-Tropsch part?
Yeah, it's a little bit sensitive to share, but I can tell you that the largest contributor is the syngas conditioning, the lumped sum of the syngas conditioning, which includes the particle filter, the Mcsc technique, and then the acid gas removal. The contribution of that section is the highest, followed by the gasification step, and the FT technique. The FT is the third contributor to the capex. So it's about, let's say, about 35% is for the gasification, and then that's a bit sensitive, but 15 to 20%, I can say, for the FT plus upgrading.
Okay, thank you.
Yeah.
So thank you everyone who asked questions, and thank you very much, Sennai. It was an interesting presentation, and we hope that this will get a continuation as well, so that you can move further and test it on pilot scale. I encourage you to go visit our website where you can find the full report and an executive summary, and then there you also find, of course, contact details for Sennai if you wish to ask further questions. And yeah, with that, we will close this webinar, and thank you so much.
Hello. One final question.
Yes.
Yeah, of course. Yeah.
May I get the report of that of this?
The report?
Yes. Is there a report of this topic? Or?
Yes, the report. I think you referred to the report from the project. It's available now. I can put up a link in the chat following this webinar, and you can go there and find all the deliveries from the project.
Thank you very much.
Yeah, thank you. And again, thank you, Sennai. And have a good day, everyone.
Yeah,
bye.
Same to you. Bye.
Yeah, same to you. Bye-bye.